periodic trends and bonding. If you remember this video from previous where we looked at two test tubes that were duct taped together, did it require energy to pull the test tubes apart, or did it release energy when you pull them apart? If you remember right, pulling things apart with duct tape takes energy, which means when the two atoms combine together to form a bond, they are going to release energy because it's in a lower energy state. And so when we're looking at that idea, we can apply it to the concept of bonding and also looking at periodic trends. So what do we mean by that is here is an energy diagram showing what happens when hydrogen atoms come together and form a bond. If hydrogen atoms are apart, they have a lot of potential energy, but you have a much lower potential energy, so a much more energy configuration, a lower energy state, if the two hydrogens come together, because when they come together, they're going to release that energy. And so they come together, now they release energy as they form that bond. But how do I know I'm at the bottom of the well? Can they not just keep coming closer and closer and release more energy? No, that's not the way it works. If you get atoms too close together, like the hydrogens that are shown here, it's no longer energetically favorable because each hydrogen has a proton, and if you put those protons too close to each other, they are going to repel, and therefore it's no longer the best the most energetically favorable situation. And so what we're looking at here is favorability and also the lowest energy state for bonds in addition to the atoms that make up the bonds. So for ionic bonding, we have something called Coulomb's law, which is just a law that's going to quantitate the amount of energy associated with these ionic compounds. And so what you see here is an equation. Energy equals 2.31 times 10 to the negative 19 joules times nanometers, and then your Q's. So your Q's are going to be your charges. So the charge on each individual compound is your Q. So if one's a +1, then the charge is +1. If it's a -2, that kind of thing. And then your R is your radius. All right. So we can easily, if we know the charge and we know the radius of the individual ions that make up a bond, we can then quantitate the energy associated with that bond. All right, now think about this next sentence. If you have an ionic bond, the energy is always, is it negative or positive? Negative. So remember, negative energy is associated with a release or an exothermic amount of energy. Another way of thinking about it is the energy is lower if the ions are joined together in a bond because a lower energy state is the most stable. All right, so we have this graph in our textbook that shows you the atomic radius, and we've already looked at it before and looked at it to predict based on the periodic trend of atomic size. But how do we expect these atomic sizes of these elements to change in comparison to their respective radii? So meaning sodium ions, we see these over here. What's going to happen when sodium forms an ion and forms +1? Is its radius going to increase or decrease? What do you think? What about chlorine? What's going to happen when chlorine atoms form Cl-? Is it going to get bigger or smaller? Well, let's look at a graph and see. So sodium went from 186 to 95. So can we say then that whenever an atom forms an ion, you always reduce in size? No, you can't, because look at what happened to chlorine. Chlorine got bigger. Well, then what trend can we possibly expect to predict here? All right, well, look at all of your anions and your cations. Your anions are over here. They form negative. So think about it this way. If you're adding another negative, but you're doing nothing to the number of protons, then what you're doing is you're increasing that atomic radius. Whereas if you take away an electron, this is where you're going to see significant decreases in size, because sodium, it would have been in what, 1s, 2s, 3s. It would have had one electron in the 3s. When you remove that one electron, you go down and you end up with 2p6. And so you went down an entire quantum number, which is going to significantly reduce your radius. So what trends can we say here? Whenever you form a positive ion, like sodium's, your ionic radius decreases. Whenever you form a negative ion, your ionic radius is going to increase. And that's exactly the trends that we will see. So how do we put all of these values in here into this equation? Well, let's look first at magnesium oxide. Magnesium oxide. So we know magnesium is 2+ and oxygen is 2-. So to put them into this equation here, we've got Q1 is 2+, Q2 is 2-. So we can put those in here. And then our radius now. So what's our radius? 65 plus 140 is going to give us 205, but that is picometers. And if you notice here, our radius needs to cancel out the nanometers on this constant right here, which means our picometers needs to be converted into nanometers. To do that, just move the decimal over 3, so that equals 0.205 nanometers. And we're able to see that this is exactly what we filled into the table here. And so if we put each of these values in for the Q's and the R, you put it on your calculator, then you should get this value here. Go ahead and stop the video and try and solve for the next 5 ionic bonds. You will notice that even if you have something like this, which has 3 atoms, your first atom is just your calcium, your second is your chlorine, because you're saying what's the energy associated with the bond between calcium and chlorine. It's not like you need to find some kind of triangular relationship. All right, so for potassium bromide, you should have said +1 -1, and your radius is 0.328. Here's calcium chloride, here's sodium selenide, and here is lithium fluoride. And so you'll notice that they each have a energy that is negative, and so that's your release of energy there. The next trend that we're going to look at is electronegativity. And so unlike the other trends where helium was shown on the graph, this is really a trend that is going to end at fluorine. Fluorine is the epitome of electronegativity. So what is electronegativity? It's kind of like electron affinity, except for it's going to have our values here, 4.0, 3.0, etc. And fluorine is the most electron-loving, and so it's going to want electrons the most, so it has the highest electronegativity value. So they're really big up here, really small down here. Electronegativity is basically how strong an element desires an electron. This is going to come into play when we're talking about bonding situations. So before, I've allowed us to kind of characterize stuff as either covalent or ionic, and not really saying that there's anything in the middle. But there's actually more of a trend. So it's not just is something covalent or is something ionic, but there's a scale that says this is a pretty ionic bond, this is a pretty covalent bond. And so with covalent bonds, you're looking for, oh, hey, is it 2 nonmetals? Because remember that definition? So 2 nonmetals. And then ionic bond is a cation plus an anion. But is there some cations and anions that act a little bit like nonmetals? Absolutely. Because you'll even notice on the periodic table there are some of the elements that are kind of right there on that stair step. And those are the ones that are going to be really close to, oh, it could be a polar covalent bond, or acts slightly like an ionic bond, but yet the bond kind of also acts like a covalent bond. So what is it? So our textbook does this electronegativity difference, or actually this is from a different textbook, but it's a pretty good way of thinking through it. The idea is if your electronegativity difference is 0, like hydrogen, where 2 hydrogens are bound together, there is no polarity about the bond. Those electrons are completely shared equally, because remember, covalent is sharing, okay? Ionic is electron transfer. And so things like fluorine and hydrogen, that's going to have more of an ionic nature, but it's still a little bit covalent, okay? So fluorine attached to a hydrogen is actually going to be like right here on the scale. So it's not a purely ionic species. Where like sodium chloride, if we go back over here to this graph, sodium is 0.9, chlorine is 3.0. So 3.0 minus 0.9, that's 2.1. So sodium chloride is table salt. That would be an ionic species by this definition. So the more electronegativity difference it is, the more unequal sharing of electrons you have, the more likely that ions are going to be formed as opposed to just polar particles. And so this symbol right here is the partial positive and partial negative. Those are partial differential equation symbols. And the idea is it's not like you form one compound entirely positive. It's kicked a lot of the electrons out to this partial negative part, and the partial negative has stolen most of the electrons. And so with this video, you've just kind of looked at the difference of some of the trends and how electronegativity or this idea of bond distance really plays into bonding.